Morning class. This is gonna have to be quick because I got work in about 40 minutes, but I wanted to get I wanted to get some sort of little review about parallel circuits out to you. This is the lecture that we would have had on Tuesday, February 5th, if not for the snow day. So I'm just making this available online so you can watch it. And if you want to replay it or pause any slides that I don't spend enough time on, you're welcome to do so. Here's one of the slides I won't spend much time on because, well, I'm hoping this has been at the start of every lecture, so hopefully everybody knows this really well by now. As for this is showing just the basics of what it means to be parallel. We have all three resistors in parallel because you have these 3 points in common and these 3 points in common. So both sides of both legs are connected. I mean, all the legs are connected on one side, and then all the legs are connected on the other side. Now remember that voltage is equal across all parallel components. So these are all parallel to the voltage source, so they will have source voltage. Here's a slide we've seen a lot, this particular breakdown, and but current is what is different along parallel branches because there's different paths for current, and parallel circuits divide the current proportionally in proportion to the proportions is based on resistance. So the greater the resistance, the lower the current. The lower the resistance, the greater the current. You'll see that the two are, it's kind of like inversely proportional. So like 10 times the resistance will equal a tenth of the current, and this one is a tenth of that resistance, so it'll have 10 times the current. Second principle about parallel circuits, the total circuit current is equal to the sum of the individual branches. So this is the symbol for parallel circuits. So later on we'll be giving you just like symbols for how to draw a circuit on your own, and this is the symbol for parallel circuits, for resistors in parallel. This is the main for at least for more than 2 resistors, I recommend using this to calculate total resistance of a parallel network. There's also product over sum, which we'll show here in a second. There's a product over sum. It's faster to do it with 2 resistors. If you multiply the 2 resistors and then divide by their additive value. Resistors of equal resistance, well, you just divide by the number of resistors. Usually there will only be 2 of the same resistor, so they would just be in half. Half of the individual resistor value would be your total of those 2. But in this case there's 3, so we divide 12 by 3 and we equal 4. This shows you how to measure the R total. R total, it will be measured from the perspective of the voltage source. Otherwise, things might get a little bit, they might have different, it would be, so if you put the meter here, you would have a different configuration. Measuring total current, it's just like we measure it in series, but the one tricky thing about parallel is you have to measure individual current values for individual resistors at times. So you just put the red into the red, the black goes into the circuit, and there should always be resistance downstream from your voltage source and your meter, and then it should have a return path back to the voltage source via the black lead. Now this is showing how to measure an individual current. So you just hook the two red leads in common and also give it a path for the other resistor. But to get to this resistor, only give it one path, and that path has to be through the meter. Comes back out the black, and it has a path to return to the power source. Redrawing a circuit. Yeah. Not going to spend much time on this. It's just kind of a rapid fire video that I wanted to put out before I had to go to work today, because I did a video for my for the math class I teach, and felt like you guys were being left out because you were ahead before the snowstorm. You were ahead of where we were last quarter. Now we're like maybe one lecture behind because we've missed 2 days in a row. Pac-Man, no need to talk about that. Self-explanatory. Pac-Man's cool. So if you were to, yeah, I'm not going to go over this again about the redrawing process. We can talk about this in class. I don't, yeah, drawing with my pen, it's a little sketchy. It's not the best pen in the world. I wish I would have bought the Windows branded pen, but I think I'm going to take it back and get a better pen. So yeah, my drawing and my writing on the screen is just a little bit distorted based on a cheaper pen. But that's okay. I got a new little tablet and I'm doing videos from it, so that's cool. You can expect more videos if we have more snow days. Like on tomorrow, I'm not sure we'll have school, so make sure you keep yourself updated. So this one is in Lab 10. So yeah, so far the ones that I've graded of this redraw have been correct, so that's good. If you need any help without a redraw, we can do that, or I could, well, I'll let you guys try to do it on your own, and if you have questions, we'll talk about it in the lab. I'm not going to redraw it here because it's kind of a drill that you guys should try to figure out on your own and see how to redraw that circuit so it makes more sense to you. Electrically common points. So we'll talk about this one a little bit. We have a series parallel combination essentially. Why is that? Well, current's going this way. It has two deviant paths, so we know that those two are in parallel, so I'm going to draw it in scripts. So we have R1 parallel R2. Actually, I need to erase that and give myself a little more room. Write it a little smaller. R1 parallel R2 plus, and it's a plus because the other parallel combination is in series with it. Why is it in series? Well, when we come over here and we have, well, let me erase that too. So after these two resistors, they come back to a single point. But then there's a divergent point between these two, right? But you'll notice that they all have a common point here, but just not, these two parallel resistors are not common on the other side. So the R1, R2 are not in parallel with R3 and R4. They're in series. So we have the parallel combination of R1, R2, which is in series with R3. Man, this pen sucks. R3 parallel R. Man, I'm just gonna write the whole thing again. That's okay. Give myself a little more space. R1 parallel R2, which is in series with R3 parallel R4. There, I made it fit. So when I put parentheses over around a parallel combination like this, it means that it is separate from another parallel combination. That's just a way to kind of break things apart and make sure and just be more accurate with your description of what circuit is drawn or what circuit you're drawing. So that is the combination for this circuit. R1 parallel R2 in series with R3 parallel R4. I'm pointing out the electrical common points, that it's common on this side. All four are common on this side, but they are not common on this side. See? That's why they're not in parallel with each other, because they only have one junction that is the same. So I believe this assignment is loaded onto Canvas. Double check that all the assignments that go with this particular slideshow are loaded, but I know most of you guys probably don't have multi-sim, so I don't expect these labs to be, completed by Thursday or something. As far as midterm, I'm thinking that if we don't have school tomorrow, we might push the midterm back from Thursday again. But we'll talk about that. We'll see what the weather report says tomorrow, and I'll send out an email. So make sure you're checking your email and checking Canvas. So KCL, here's the new concept. Kirchhoff's current law. That means that Q2 plus Q3 will add up to equal what went into that parallel junction, which was Q1. The algebraic sum of all currents entering and exiting the node must equal 0. So here we have pretty self-explanatory slide. Don't confuse the number locations with being nodes or junctions. It's just these are all actually the same. So now we got the current divider formula. I told you it was coming, and now here it is. So what you'll notice how it's different is you still multiply the total current just like the voltage divider formula. You multiply I total instead of V total, but you put the R total on top with the current divider formula. Notice the R total goes on bottom with the voltage divider formula. So that is because you put the R total in the numerator for I total, the current divider formula, because R total is going to be less than Rn in a parallel network, and you have to have less than total current, so the smaller one has to go on top. Looks like it, hold on, next slide. So yeah, I was going to do this one as an example to show you, so I left myself a bit of space. So that's good. So I'm going to calculate real quick. I didn't do this ahead of time, so just give me a second. So I'm going to calculate R total. So RT equals, let me get on my calculator. We got just one moment. I'm going to put it on pause. So our R total is 5 point, oops, not an R. R total is, come on, erase. There we go. Our total is 5.7 ohms. So for I total, we do, I can't show all this work because I won't have enough space to do it and do the current divider formula. So just trust me that your I total equals 2.1 amps. And we came to that by dividing your V total, which is 12, and you divide that by 5.7 ohms, and you come up with 2.1 amps. Next step is we do individual branch currents, because we know that all of the resistors will have source voltage of 12 volts. But what's IR1? So for that, you do the 2.1 amps times 5.7, the total resistance on top, divided by 10 ohms. Haven't calculated that one yet, so just bear with me for a second. I will. So we got 1.2 amps. So IR2 equals the 2.1 amps times 5.7 in the numerator again, and then 20 ohms on top. Let me put that into my calculator real quick, and survey says about 0.6, and I'm rounding these a little bit. I rounded the first one, I've rounded them both up, but it's pretty close. So I have 600 microamps, but we'll write it as 0.6 amps. Actually, I meant 600 milliamps. So if we have 1.2 amps and a 0.6 amps, so for IR3, we could just do it by subtraction of the 2.1 minus 1.2 and 0.6, but that won't serve the purpose of this lesson. But so let's just calculate it this way: 2.1 amp times 5.7 ohms divided by 40 ohms. We know that's going to be the remainder, so I'm not even going to plug this in my calculator. It's going to be IR3 equals, what are we at, 1.8, so 0.3. 0.3 amps is our remainder. Let's see if we got it right. Yeah, they just rounded it different. That is approximately equal to 1.2 amps. That is approximately equal to 0.6 amps. And that is approximately equal to 0.3 amps. I just kept it all in the same range of yeah, I didn't use proper engineering notation like you guys should. I just wanted to, for the purpose of that lesson, leave them all as a portion of an amp rather than, yeah, anyways, breaking it down to milli. So yes, so this is just showing that in parallel networks, that power configurations, that they're still additive and that it still works. It's I'm running out of time, so gotta kind of move forward a little bit. So we can talk more about we will talk more about power configurations and maximum power transfer and stuff later in the quarter, but right now we're just basic power calculations is power equals I times E, and it's really not much different in series and parallel. They're both additive in any configuration of a resistive circuit. Just a couple more slides, then I gotta go to work. We're supposed to leave right now, actually. But that's okay. I just wanted to get this video out so you guys had something to look at and review. So this is another power example. Here's assignment 24, which I will load a little later. I gotta go to work, so. And I'll load this one too. I'm not expecting these to get done right away until we start getting back in the lab, but you know, I know that a couple of you have multisim, so I will load them into modules. For the people that don't have multisim, don't panic. We'll get there. So, what's new? Well, this is series parallel concept. Well, And that's where we'll leave it. We need to get into series parallel, probably not till next week, but maybe a little bit on Thursday. I don't know. We'll see. I gotta go to work, so I hope this video is helpful as a review to parallel circuits and as an introduction to the current divider law. I kind of went through it fast, but I spent as much time as I had, even just a couple minutes more. So have a great day. Hope this helped.